So let's talk about functional data structures and Java 8. If you have any questions, please post them to the RC channel. Roberto will be monitoring that and hopefully will interrupt me at every opportune moment, or if you are present at the jogs that are currently with us, so Peru jog and Silicon Valley jog, you can also interact with me as if we would be in the same room. Oh, the power of technology. How nice. How nice. So let's do this. So this idea of this session started when we at Zero to Round were doing an infographic, a cheat sheet, if you want, about Java collections. So I'm a developer advocate, and I often maintain and write blog posts for Rebel Labs, which is the blog Zero to Round publishes at. And this year we started doing the cheat sheets, where we try to put as much information as possible into a one A4 image. And at some point of time, we started thinking about, oh, let's do a Java collection cheat sheet, because there are so many implementations. They all have their trade-offs. They have the complexity and how fast the access is. There are third-party libraries and so on. And we did that, and we published it on the internet, and you can access that if you just Google for it. But then at some point of time, the response was, oh, some people were really kind of not sad, but really disappointed a little bit that the functional data structures or persistent data structures and so on were not represented as well as the others. And since then, I figured out that maybe we should talk more with developers about the existence of functional data structures and talk about other fundamental details about what powers our collections. And collections are found in every application. There is absolutely no way, almost no way, to write a meaningful application without using collection. You will use a list or a map somewhere. And that's how the session started. And obviously, to start this session and start gathering information, I wanted to kind of poll the public opinion. And I asked my followers, what does the functional data structure mean to them? And give them a set of choices. So either it is not dysfunctional, meaning that a functional data structure is the one that works, a very literate meaning of the functional in the name. It is not imperative, meaning that is more from the functional programming word. It is a persistent data structure, which is a vague, it's a very rigorous name if you know what a persistent data structure is, but it's a very vague option in this poll. Or that is just allows mapping functions over the elements in that data structure. So kind of like a typical collection, but with the functional programming parts as well. And the response was very diverse, and people, I'm not sure though, so there are like not that many votes. Maybe people were not that interested in data structures, but even then they didn't agree on a single choice. And to be honest, this was a tricky question. I think a functional data structure would be all of those things. So, but it also showed that people do not either just wanted to troll me, or they do not properly have an idea what a functional data structure is. And
Oleg?
Yep.
I think you're not sending in your slides, so can you switch to the slides, please? Sorry about that. Now? Sorry interrupting you.
No worries. What about now?
Yeah, she'll be. Well, click the slides screen.
Can you see Ted?
Yeah, we can see Ted, but not as a full screen. Well, we see you as a full screen. Well, try it now.
That's very unfortunate. Live. Let me. Yeah, I think the video shows Ted properly. So if you look at the YouTube video, as the our viewers are looking at, then they should see the picture of Ted. And why I wanted to refer to him is that he gives an excellent session on what a functional programming is, because the functional programming and functional data structures a little bit different concepts. But in his session, he talks about how functional programming opens a different set of tools for developers. So it's a set of paradigms and ideas that you would be able to use if you train to use them. And with some experience, you'll be more and more proficient with them, and you will be able to use them more and more efficiently. The same thing goes with functional data structures. It could be a strange idea, and during this session, you might be having this initial response in a way that, no, this shouldn't work, or this would not work for my use case. But just think about this way. This is a tool, and there are people who find this very useful. And at some point of time, you might find a problem that requires that, or for which functional data structures are perfect. So you are better with knowing about those things existing. And data structures are not a new topic. And obviously, it started like 40, 50, 60 years ago when we started imagining programs, and it grew with computer science through ages. And there is a saying that, well, through all that research, we started making data structures very, very efficient, both in memory and both in performance-wise. And the saying went that you can use any language or any style of programming for fast and efficient data structures as long as they're imperative. And for a long time, that was really true, because imperative data structures were kind of fast and functional lagged behind. But this is not longer the case quite a bit. And to understand the whole evolution of data structures, we will need to look at several examples. So obviously, you know that the JDK, the standard JDK library, packs quite a set of collections, pun intended, for you to use. And most of those collections, and data structures that are powering those collections are mutable. So a perfect example of that you will find in the interface collection itself. You will find, among other methods, several like void clear or Boolean add all. And the thing is that if you find a method in your code base as well, which return type is void, or Boolean, or something that is not actually the proper set of data itself, then most probably this method operates in a way that it creates side effects. So there has to be some state that calling those methods will modify, and they will mutate that state, and they will return the result, not the result of the data, but they will return a flag, or they will return nothing to you, but just modify something else somewhere else. And this is a fine approach. However, it might introduce a lot of mistakes in your code, and when you are in a concurrent environment, it might be hard to reason about this. If you will need to guard your access to the mutable collections with synchronization primitives and so on, and that might not be the most maintainable case. Even in a single-threaded program, you probably can stack clears and add alls and retains and other methods from the collection to the point when the program will become much less readable, because to follow that and reason about the program, you as a developer have to maintain the state and in what is happening to the collections powering your data structures at every moment. So with every call, it mutates, and it's hard and challenging. Luckily for us, there is a second step on top of the mutable data structures, which is could be quite fast, and it's easy to implement them, and we have a lot of research on that. We have the immutable data structures. So the immutable data structures are those which cannot be modified through their API. So in the JDK, you have a set of wrappers, and you can use collections, say unmodifiable list or set, and give it a collection, and you will receive an object that is also a collection, but any mutating methods on that would throw an exception. So you will not be able to modify the data, and then if you deal with just that collection, reasoning about the state of the elements in that collection is much easier. This is not the perfect, maybe not the perfect implementation of the immutable data structure, because the underlying collection, the other list on the slide, is still mutable. So if somebody gets access to that and shuffles the elements, you will see the shuffled elements in your view on that collection, despite that being unmodifiable. So it does not create a copy of that. It just provides you with a wrapper that disallows some methods. Then this next step of the collection hierarchy here will be persistent data structures, and this is a much more interesting set of collections and data structures. Persistent data structures are those that give you access to all their states after you modify them, after you use an operation that modifies their state. They will give you access to both instances before the mutation and after. So you would be able to go back and see what that data structure was at every point of its life. And naturally, you can achieve that with just copying all the elements, the full data structure. So if you have a tree, you can always copy the whole tree and just modify that, the copy, which is fairly inefficient from the performance point of view. And that would be one of the main topics of this chat today. So we'll talk about performance a lot. We'll talk about how to make operations on the collections as efficient as possible without losing properties like persistency. So for the persistent data structures, the typical approach is that you do not copy the whole collection and modify it, but you modify just the necessary bits, and you will reuse as much of the structure of the underlying collection. So if you imagine there was a black tree that you can see on the slide, and then you will need to modify that somehow, for example, add the E element below the F, then you would modify and create one branch of the tree that is necessary to create that which will be different, but you utilize the substructure of the existing collections. So the subtree BAC is the same in both collections. So you do create more elements, you do use more memory, but you don't just straightforwardly in a naive way copy elements. And the goal for that is that you can access the previous version of the collection easily. And the functional data structures is a different beast, and it's a very cool thing. It is a collection that is both immutable and persistent. So you cannot modify that after you create that, and you also, all the operations will return you a new view on the collection, and it will try, all the operations will try to leverage the substructure of the existing data structure that you have. So if you have that tree, and if you cannot modify that tree directly, and all the operations are giving you new trees back and allow you to access the previous tree again, that would be a functional tree. And there are many ways how to do that, and we will go right into the code and see how to create some functional data structures right from scratch. So there is a couple of challenges. You cannot use assignments after you created the data structure. Since it's immutable, you cannot just modify the elements or point to another node somewhere. And you have to always remember that you need to think about persistence. If you think about the most primitive data structures that you would like to build, most probably that would be a list. And I really hope that you've seen an example of a list like that in some other language at some point of time. If you don't, it's fairly simple. The functional implementation of a list data structure typically is called cons, and it consists of two things. It consists of the head element, which is the element head here, and it consists of a list which represents the tail. The tail is all the elements of the list besides its head, and it is also typically would be a cons list. So with those elements, since the list is immutable, you can add additional information right into the structure of this object. So for example, we can always add the length attribute right there, because we know since our list is immutable, once we set the list lengths, we will not change the list, and thus the lengths will always be the same, which is a fairly cool property because it makes having access to the list lengths very simple. Now, the question here would be how to implement typical list operations on this data structure, because we don't just define it. We would like to use that in our code. So prepend is a very often used, frequently used operation on the list. And what you do to implement a prepend, you just create a new list. The element that you want to be at the head of the list becomes the head of this new list, and you reuse the whole existing list as the tail for the new one. So you can see that the implementation of this method does not in any way mutate this instance of the list, and it creates a new list. So you will have access to both states of this list that you have of this object before prepending and after one, because you will have two different cons objects and you don't mutate the list. So both properties is satisfied. So prepend is our cons list with prepend is still a functional data structure. The next thing to see is that this operation just creates one object, so it should be fairly efficient because, well, it's very fast. Create an object and add a couple of pointers. Imagine if you want to prepend to the list again, you will get the same the picture like this. So if you had list of 2 and 3 initially, and then you prepended 1, so it started to be that, and then you have access to the old list again, so you can prepend 0, and you will have 3 new lists, and they will reuse the structure of each other as much as possible. Now you can do a much more complicated operations, like for example, you can fold the list. Folding a list, if you don't know what it is, it's like folding a carpet, putting a tiny item on one end. So you iteratively, you progressively go through all the elements of the list, and you apply a given operation, the fold operation on this slide. It is the FB function from elements to elements, and you repeatedly apply that to the 0 element, which is the result of the previous application. So you can see here 2 things. First, if you are interested in generics or unconventional uses of generics, then collections libraries and the code for data structures is the perfect thing to look at, because it's written with all those covariance, contravariance definitions for the collections, because they want to be as generic as possible. And the second thing that you notice that inside our methods, we use the mutated operation. So in the implementation of the fold function, we can reassign the value to the XS element without mutating the state of our collections. So when you think about that, about the fact that immutable means strictly immutable and you cannot use assignment, that is not strictly true. But you can fold a list, and the thing is to notice that it has to traverse all the elements. So its execution time will grow with the list size growing as well. If you would like to reverse a list, you would use this fold operations and the existing prepend operation, and you would utilize it like that. So again, you just create new lists, and then you traverse the list and you start building it from behind using the prepend operation. So reversing a list is an expensive operation because we use fold left, which has to go through all the elements. So reversing a list is, as they say, an ON complexity, a linear complexity of the list side, which is way more than the, say, prepending an element to a list. And we'll come back to that in a second. Appending the element to a list. We've seen prepend, and prepend was easy and nice. And appending to a list, a functional list, is not as easy. To append to an element to the right, on the right, you have to go through all the list, through all the elements, and that will take time. So this shows that despite functional data structures being all cool and shiny and nice, there are use cases where you would actually have to think twice if you would like to use a particular data structure and if it supports the operations that you want with the performance of that you need. So appending an element to a list is an expensive operation, and prepending is really cheap. So now, still, all those implementations, all those methods are taken from a library which we'll see in a little bit later, and they are proper functional code. And the list of cons with the operations like prepend, append, and folds and reverse implemented like this is a functional data structure. So you can do a lot of things with that. And one of the things that we want typically do with data structures is to build different data structures. But first, we'll need to talk about algorithmic complexity. If you have background in computer science, you probably know what it is. If you don't have a background in computer science, there is a cheat sheet for you. Algorithmic complexity tells you how long, in theory, a given function would run. And there are orders of magnitude, so to speak, orders of magnitude of the assessment if the function will run short or long time. Since the input to the function, when we talk about abstract functions in the vacuum, is not fixed, we would like to talk about how long it will take with respect to the lengths of the input. So if we have a list with lengths n elements, and for example, prepending the element would have a constant complexity. It would be O1 because we do not have to do anything, and in constant step or constant number of operations we're done. Reversing the list or folding the list will have the linear complexity, and it will mean that we need to go through all the elements, and thus we will need to do kind of n times some constant operations. And then there are more positive complexity and slower complexities. So there is a whole universe that goes below those on the slide. So we have a quadratic complexity, which means that we'll have, for every element in the list, we'll have basically traverse the list again, and we'll do n squared operations. And you can go further and further. So it's a very fascinating area of research. Why are we talking here about this? Because we would like to talk about performance of data structure, of functional data structures, but without actually showing you the real code, pieces of code, and benchmarking that. We would like to theorize about what is happening and why those data structures should be fairly efficient. And this is how actually to properly do that. Now, the next thing that you should know is the amortized complexity. If you don't know what it is, I will just give you a very short introduction to that. Imagine you have a bulk of like a set of operations, and you do the operations in batch, and you would not really care about the expense or the performance of the individual operations, but you know that you would do all those operations together, and you want to reason about the complexity of those elements all together. And that is the amortized complexity. You kind of spread the complexity of all operations together through a set of operations. Why is this cool? Because you can do an amazing things. So imagine you have this batch of operations. You have a list, you construct a list, and then you prepend a bunch of items into the list, and then you reverse that. So individually, we know that the complexity of prepend is O1, and the complexity of reverse is On, which is the linear because it has to go through all the elements. But now we are really interested in the complexity of the whole set. And there is a method to how to compute that. It's called typically the BANKER'S method. What it does, for all operations, it assigns not just the complexity of that operation, but a little bit extra. So imagine when you execute an operation, it just gives you a little bit of credit to execute a more expensive operation later. So if we add that tiny alpha to all the constant operations in this set, then the total complexity, if we just sum it all up, we will have something like this. So we will have 2n plus n times alpha. And we can simplify that using the rules of mathematics. And then we can simplify that further using the rules of big O complexity. So we will throw out the constant because we do not care about the constant yet. We just care about the order of magnitude compared to the size of the input, and that size is n. So we care about n. And then our complexity, if we divide that by n, because we have n operations here, then per operation complexity would be also constant or very close to constant. So the amortized complexity tells us that if we have a lot of prepend operations and then one reverse operation, then in total, it kind of all evens out, which is an amazing property, which we will use to make our functional data structures fast. functional data structures will make it hard a little bit because you have the expensive operations. And since you have persistent data structures, you can call expensive operations again and again and again, and you will not have this extra credit of the performance budget that your short and inexpensive operations create you. So if you call expensive operations often, you will throw out all the theoretical calculations. So what you need to do that to avoid that, you will need to have lazy evaluation, and you will have to memorize the results. So since we know exactly what is the result of the given operation on the given data structure, because it's immutable, so we cannot change, we cannot get any other result, we can memorize that and we can reuse the results from cache. So having a lazy implementation with memorizing the result will make your data structures much more effective, and will help you use amortized complexity to reason about the performance of those things. So since we've seen a list, now we are ready to build a queue, and we will build a queue using a list. I don't know, do you have an idea how to build a queue when you have a list? You can, in the Silicon Valley Jog, if you have an idea, you can raise the hand. I can see you right now. How to build a queue when you have a list? Okay. Fair enough. It's not the easiest thing to do. So if you have a list, you build a queue like that. The only thing that you have is a list. So you take the list and put that inside of your queue definition, and you are done. So essentially, since we have the prepend and append operations on our list, we can create the operations for the queue. So a queue is the first in, first out kind of data structure. So kind of like when you wait in line for Starbucks or a bakery, first comes, first served. But in a sense, it would be fairly inefficient, because accessing list from the front is cool and nice and fast, but accessing list from the back when you want to append elements is fairly expensive operation. So we would not build our queue like that. But the only thing that we have here is a list, because we only know how to build a list before. So to build a functional queue, we actually will have two lists, and we will call them the front of the queue and the rear of the queue. And this would be our queue with two lists. The trick here is that the elements in the rear of the queue, the elements in the rear list, are in the reversed order. So the very tail of the queue will be at the head of the rear list. That trick, this simple trick, will give us access, very fast access, to both the front of the queue, which is the head of the front list, and the tail of the queue, which is the front of the rear list. And this amazing trick gives us an idea how to implement the queue now. So imagine you have a front and the rear, and you want to enqueue an element. You want to add an element to the tail of the queue. Then what you can do, as you cannot modify the existing queue, you create a new object, you create a new queue, you copy the whole list. Well, you reuse the whole front list because it doesn't change. So you reference that. And then to the list that is rear, you just need to prepend this single element, and you return this new object. The cool thing to notice here is that the complexity of this operation is constant again. We create one new object, and we just reference other objects. Well, we create two, because prepend an element to the rear will create a new list for us. But still, it's a constant type of operations. Now, if we would like to take the tail of the queue, which is everything besides the head, and this would be our utility operation, then we create a new code, a new queue that has the same rear and just has all the elements from the front except the first one. And now it's also a constant time operation, and very useful, because we can now peek. Oh, if we could peek before. So to peek in an element in the head, we just see what's in the head of the front list. Fairly simple. If the queue is empty, though, we will have to throw exceptions, which is a little bit sad. Exceptions are sad. But the actual implementation, the front.head, is very straightforward. Now, dequeuing operations is a very interesting one. Dequeue is a mutating operation, right? We change the underlying structure of the queue. We inherently just separate the head of the queue from the entire body of the queue. and we will need to have access to both. So first, you will see that DEQUEue operation on a functional queue will not follow the interface that your Java collections define. So in Java collections, you have a queue implementation, and it follows the queue interface. But unfortunately, since we have to provide both the return value and the new state of the queue, the functional queue cannot follow that interface precisely. So if you have a queue of 1 to 3 and you want to DEQUEue an element to take the first element away, you will have to return an element itself and the new state of the queue. However, this API is fairly straightforward again, and you will have access both to old queue and the new queue, which satisfies our persistent property. And the implementation of DEQUEue is fairly straightforward. What you just have the head element, which is the first element of the queue, and you have the tail of the queue, which is everything else. And you just wrap that in tuple. Fairly straightforward. Now the question becomes like, are we sure that the front is empty? Will that mean that the rear is empty? Because when we want to DEQUEue an element, and if it's empty and if the front is empty, we will throw an exception. However, we will use a trick, and the front is empty will mean that the rear is empty. We will introduce an invariant to our code, and we will make sure that this invariant holds. One cool thing about data structure is that we only need to consider when this invariant only when we create the data structure. Because it's immutable, we don't change that. So after the fact, after it's created, we never have to worry about the invariant again. So our code will be complex in the constructors, and it will be very, very simple and very efficient in the method implementations. So the trick is here, if the front is empty, we will need to use the rear as the front list. And since the rear is in the reverse order, we'll have to reverse that. And then we just either use the proper rear or the empty list for the rear itself. So the thing is here that we use this reverse operations, and that is an expensive operation. It is linear in size of the queue. So it will go through all the elements, and that might be quite inefficient. However, imagine this situation, and here the amortized complexity comes to help. If we have a queue that has m elements in front and m elements in the rear, we will need to hit the code that does the reverse operation. To use that code to hit that use case, we will need the front to be empty. So we will need to remove at least m elements from this list, which is the constant time operation. And then only we will look at something and we'll need to reverse the rear list with m elements. However, as we saw on the amortized complexity example, if we use a constant time operations m times, and then we will use an OM operation, the amortized complexity will still be constant. So this invariant holds, and there are mathematical proofs how to do that, and it's a magnificent thing. So from a very simple list data structure, we could build a immutable and functional queue data structure, and that would be efficient, and that would be fairly performant and fast. And we do that by designing it carefully and using mathematics to prove our point. Now, using queue and a list, do you know how to build a map? And we are fairly short on time, so I will not ask those questions from jobs that we have. The thing is, building a map is way different from building a queue. A map is an inherently different data structure. It has different elements in it. So there are keys, the values, and the structure is different, and it's very unlike a queue. So to build a map, especially the functional map, you will need something other than the list or the queue. So typically, you will have a hash array mapped tree, where the tree is what you spell with TRIE, or sometimes it's called the prefix tree or the suffix tree, one of the trees. So the thing is with the HAMT is that it is a tree, but the elements that you hold in that map are the leaves in that tree, but the keys are not stored anywhere, but parts of the key are mapped into the relationship between the parent node and the child's node. So the path from the root to the leaf node will be the key that leads to that value. So if you imagine, if we talk about how to access the element by the key that consists of blue, lilac, orange, and green, then we take those parts and find which children of the root node we need to take. So we see the green and we take the green node, and then we see the part that is orange and we know where to go further, and then the part that is violet or lilac or whatever color it is, and we go further. Imagine if you have just the key that is an integer, and the integer consists of bits, then every node in the map could have two children, 0 and 1, and depending on which bit are you looking at, if you have 0, you go to the left, if you have 1, you go to the right. And then at some point of time, you will go through the whole key and you find the element that you're looking for. Or you will not find an element there. That will mean that there is no such element in the map. If you think about this, that this is fairly inefficient, this is what you have to go through all the bits, then consider this. The tree will be at most 32 layers deep, and 32 is a constant, so the operation will be seriously inexpensive in terms of the complexity. If you want to modify a map built out of the tree like that, you will need to create a copy and utilize as much of the structure as you possibly can. And this is the slide taken from Rick Heike's slides. He's the author of Closure, the JVM language, and they have the immutable data structure there, and they use those exactly like this, and they serve the Closure developers really well. And there are implementations of the functional and persistent data structures in Scala, and all this good and nice, but, well, it was lacking in Java world for quite a bit. However, now we have the solution for the Java programs as well, and we have the many libraries. Actually, we have several libraries that implement functional data structures or that implement persistent data structures, and my favorite out of those is JavaSlang. I know that there is the P collections is the different library that implements the functional collections or the persistent data structures, and there is what is the functional Java library that also implements the data structures in a functional way. But the examples in this session are taken from the JavaSlang, and it's a nice library. They are very actively developing that. It's available on GitHub, and you should check it out. Besides the collections, it has like quite a lot of goodies inside. But if we talk about the collections in JavaSlang, we have very many implementations of collections that you would like to use in your code. So you have tree maps, and you have hash maps, and you have even the linked hash maps where the order of iteration is set. You have the sets, and you have the list, streams, and queues. You have vectors and arrays. So you have the full set of the collections that you would like to use, and all of those are implemented in the functional style. And you can just drop the jar into your project and be happily using that if you would like. It will make your code probably more readable, and it will make your code easier to reason about, not because of the virtue of the JavaSlang, again, despite the fact that it's a very cool library, but just because your data structures will become immutable and functional. So you will always know what is inside any of them at any point of time. And you will never get surprises about somebody else modifying your collection and you finding and experiencing weird bugs or weird errors because the state of your collection is not what you thought it was. So it's quite useful, and several projects use that, and they are happy about that. And you maybe should take a look. The examples, the code that you saw on the slides is taken from JavaSlang, and you can see that it's very readable, so that you always can see and look how the operations are created. And if you worry about performance, and probably you should, because it wasn't an accident that we talked about algorithmic complexity and all the rest, all the other things, and we tried to reason about that because performance is important, and changing such a base, a cornerstone thing in your application as the collection library could have an enormous impact. So one thing about JavaSlang, which is kind of cool, is that it comes with a set of benchmarks, and they kind of compare on a different set of operations, different implementations of the collections. So they use the mutable collections from the JDK, they use the collection in Scala, the Scala Z, the immutable collections in the JDK if they have the implementation there, and they try to make a fairly independent and reasonable benchmark. So if you consider an example here, they use JMH, so they use the Java micro benchmark harness to create the benchmarks, which is a good sign. So that's not a hand-rolled benchmark, so they by default they are insured from doing quite many mistakes that benchmarks do. Of course, it doesn't mean that their benchmarks are pure gold, so you have to check for yourself, but they are fairly reasonable. So if they run on different sizes for the data structures, and they set them up, and if you think, for example, of a benchmark for one operation, they do it a little bit like this. So they have a set of elements that you want to do, and they benchmark a set of operations altogether. So for example, this benchmark starts with the empty priority queue, and priority queue, which is a very fascinating collection that gives you not the first element that was in the collection, but it gives you the cheapest element in the collection by some comparison. So they enqueue all the elements, and they see what's the timing for that, and they assert things and do that, and they check the DEQUEue. And I'm showing this benchmark because I wanted to show you how to use the API properly. So imagine you have the collection of values of integers. When you call the DEQUEue again, you will get back a tuple. You will have two elements: the result, which is the first element in that, and you will have the next instance of the queue that you'll have. So you'll have to assign that back to, if you want to just iterate that with a while loop normally. So, and you can see even more expressive benchmarks that they have. For example, you can sort elements with the priority queue, and it looks a little bit like this. And we won't look at the code here because we're out of time, but definitely go check out the library on GitHub. It's an interesting code. Now, if we talk about performance, they have the results, and those are the numbers that they had in, I think, late June this year, and they improved a little bit, and maybe they introduced regression here or there. It's the vendor benchmark, so take the numbers with a grain of salt. I just wanted to show you here the order of magnitude. So those are the ratios between the times that it took for different implementations to do the operation. And you can see them in numbers, but to sum them up, the priority queue implementation in JavaSlang could be about 5 times slower than the mutable Java version, that the mutable priority queue in the JDK. It's also a little bit slower than the mutable version in Scala, but it's also faster than the functional version of the priority queue in Scala Z. So the takeaway here is that there is a performance cost that you will gonna pay if you switch to functional collections, but it's also not that large. So typically, if you have a slowdown of order, like of magnitude 3 or 4, it might be a big deal for you, especially if you're running at the top of the resources that your hardware offers you. But then if you think about the difference between the optimized, heavily optimized, say, C++ code and some just maybe naive or semi-naive written Java code, the order of differences could be also like 2 or 3. If you look at the, I don't know, programming languages benchmark game or something, differences like 2 and 3 times is not that unexpected. So if you can pay that cost and use Java, then maybe you can pay that cost again and use functional data structures. It might not be acceptable for you, but who knows? Maybe it is a good thing to pay for having your code more readable and more easier to reason about. So keep that in mind when you check that out. And just to conclude, functional programming is a very nice concept. It tries to make code understandable and easier by minimizing the moving parts. So it tries to discourage having global state or mutable state, and functional data structures use that concept and push it even forward. So they want you to be able to reason about your collections by minimizing the moving parts of that. It probably will have some overhead and garbage collection impact, but most probably it would be quite reasonable. So with that in mind, if you want to know more about data structures, there is no better place probably to start than is to read the Purely Functional Data Structures book by Chris Okazaki. And he has written that in, I think, 1998. So what, 20 years ago, almost 20 years ago. And well, actually 20 years ago. Whoa, time flies. So, and it is based on his PhD thesis, and he goes through all the definitions and proves how to use them and why the functional data structures work this way, why they're fast, and it has the definitions why they should be lazy. And it's very fascinating to read if you are into that sort of thing. It's a very good book. And if you don't like books, but you are a more modern developer and you prefer Stack Overflow kind of sites, there is one Stack Overflow answer that is absolutely mind-blowing, and that is the answer to the question, what's new after that Okazaki book was published, so in the last 20 years. And that is the answer that spawns like 2 pages and comes with links to papers and articles and explanations and the implementations of all kinds of cool things like finger trees and zippers and other cool data structures and collections. So maybe if you're not ready to read the book like that yet, maybe you should look into that answer and go through links. And if you're interested in functional data structures, that could be a very good starting point. And I think that is it. My time is up, and my content is up. So I think we are done with the presentation. Do we have any questions?
Any questions? Any functional questions? Keith, you have a question. Come on. No? Nobody has any questions?
Do we have any questions on the RC? Roberto? Oh, come on. Kevin, ask me a question.
Checking it now. Give me a sec.
Oh, thank you. Thank you, Roberto.
So I also think for the folks here in Mountain View, it might be good if you can give like a quick 30-second overview of VJUG and if they like events like this, where they can go to see more.
Thanks. That's a great question, Kevin. So VJUG is an online-only Java user group. So you are members of the Silicon Valley JUG, and yeah, you are lucky that you have this access to the content and the sessions that they provide. But if you are located further away from a JUG that is fairly active, then what you can do, and by all means, even if you are close to a JUG or a member of an existing JUG, Virtual JUG is an online-only community of Java developers. It's just like regular Java user group, but it's located online. So you can join that from your home, from the comfort of your home, and twice a month we try to run sessions by the wonderful speakers that we can find from the world-class speakers, and we have this advantage over normal JUGs because we are online only. So we don't have to fly them anywhere, but it's really easy to get them to do a session from their living room. So twice a month we try to run that, and you can join that and watch the session just like you watch this one, but it will be one individual session, not the full 24-hour day. So you can join that. Typically it runs at, oh, I'm bad at time zones. So it runs around like 5 p.m. London time, which is about, I think, 4 p.m. UTS right now. But it also, well, juggles because there are winter time and whatnot. But it runs somewhere in the evening.
It usually starts 5 p.m. UK time, which is usually plus 8 hours or less 8 hours in the
Silicon Valley?
Pacific time zone. Yeah.
Yep.
Or or depending if that's like winter or summertime, might get like 7 hour difference for like 2 or 3 weeks.
So I'll add that, like, generally speaking, I've been watching the VJug for a while now. But generally speaking, at least my opinion is that they have like definitely slightly better speakers and lineups than us. So they definitely they run a good show. They're able to pull great speakers from all around the world. So definitely recommend you check it out.
Thank you so much for your kind words, Kevin.
Kevin, I know that was hard for you to say, but we appreciate the sentiment. Yeah, the being online only is a huge advantage, and indeed we can reach into the storages of knowledge and wisdom that other JAGs cannot very easily do, even as cool as the Silicon Valley. So virtualjug.com.
Sorry, we still have. We haven't time to talk about the VJug. I wanted to do some questions here, actually, relative to the session that are coming here from the IRC. So MPA Steven is asking, should we implement this kind of acts to obtain faster speeds with specific operations, or will the risk outweigh the benefits of it?
Sorry, should we implement what?
So should we implement these acts to obtain faster speeds with specific operations, or will the risk outweigh the benefits of it?
Well, it depends. It always depends. You can certainly try looking at stuff like the operations here or the data structures. You can implement that at home. Probably you would like to use a library that already implemented quite a bit of the functionality for you, and it depends totally on your definition of a risk. If you're running a real-time system that absolutely cannot sacrifice any performance, if you are a machine in a hospital that controlled the heartbeat of thousands of patients, probably the risks outweigh the benefits. Then again, maybe the functional safety and being more able to reason about the program will overweight the costs. If your programs deal with other people's money, then that is one case. If you're running a web server that streams movies to people, then it might be a totally different story.
Great. I think we should wrap this up. Have like a couple of minutes break, and so we can start the next session.
Yep.
Any other questions from the room? Best question?
Your traditional panel